Monty Hall problem, a contestant is presented with three doors, one of which has a car behind it, and the other two of which have goats behind them. The contestant chooses a door, then the host Monty Hall opens one of the other two doors to reveal a goat. The contestant is then given the opportunity to switch that choice to the remaining unopened door or to stick with their original choice. The usual question is, what is the probability that the car is behind the contestant's chosen door? And the answer to the question is that the probability that the car is behind the contestant's chosen door is 1/3. The probability that the car is behind the door offered by Monty is 2/3. Most people find this counterintuitive, probably because we naturally expect symmetry in such situations. We expect that the information provided by Monty opening a door either affects nothing or affects both unopened doors equally, but not in this case. After studying this problem, I realized that the opening of the door affects the door that Monty offers to the contestant, but not the door that the contestant has initially chosen, which led me to the crux of the problem, the statistical independence between the contestant's choice of the door with the car and Monty's choice of the door with the goat. To greatly aid in remembering and help in presentation, I will provide some notation. 1. AC is the event that the car is behind A, door A. BC is the event that the car is behind door B, and so forth. AG is the event that Monty opens door A and displays a goat. BG is the event that Monty opens door B and displays a goat, and so forth. P at X is the probability of event X. P at X bar Y is the probability of event X given that the event Y has already occurred. Now let's prove the independence of the event AC, the contestant's chosen door, and the event BG, B is the door opened by Monty, using the technique of proof by contradiction, by which we assume the opposite of what we want to prove is true and derive a contradiction. Assume that the events AC and BG are not independent. That is, the probability of AC given BG is not equal to the probability of AC. By the law of total probability, we have the probability of CC equals the probability of CC given AG times the probability of AG plus the probability of CC given BG times the probability of BG plus the probability of CC given CG times the probability of CG. Since the probability of AG is 0 and the probability of BG is 1/2, we have the probability of CC equals probability of CC given BG divided by 2 plus the probability of CC given CG divided by 2. We know that probability of CC given CG is equal to 0. So the probability of CC equals probability of CC given BG divided by 2. By Bayes' theorem, we have probability of BG given AC equals the probability of AC given BG times probability of BG divided by the probability of AC. We know that the probability of AC equals 1/3 and the probability of BG equals 1/2. So the probability of BG given AC is equal to 2 times the probability of AC given BG. Assuming that AC and BG are dependent, we have probability of AC given BG is not equal to the probability of AC, which implies that the probability of BG given AC is not equal to probability of BG. Since the probability of AC equals probability of BG, Combining these last two steps, we get probability BG given AC is not equal to 1/2, which is a contradiction. It contradicts the fact that Monty only opens a door that doesn't have the car behind it. Therefore, our assumption of dependence must be false, and so AC and BG are independent. By symmetry, we can also conclude that AC and CG are independent. Hence, the probability the event that the door chosen by the contestant hides the car is independent of the event that the door opened by Monty reveals a goat. Now, since AC and BG or CG are independent, the probability of AC given BG equals the probability of AC, which is equal to 1/3. Therefore, the probability of CC given BG equals 2/3. This is our result for the problem itself. Now the question is why these events are independent. It follows entirely from the probability of BG. We know that probability of BG must be 1/2 because AC is true. If AC is true, Monty has an equal choice of doors B and C to open. And if CC is true, Monty can't open A, but must open B. Thus, there is no choice. Monty must open B and the car is behind if the car is behind C. As we can see in the proof above, this forces the events AC and BG to be independent because the probability of BG given AC equals 1/2 and probability of BG equals 1/2, which means BG given AC equals probability of BG, since they're both equal to 1/2, which is the definition of independence between AC and BG. A better, more intuitive way to see this is to realize that if the contestant picks door A, then Monty can open either door B or C, and it does not matter when the car is behind A which of the two doors Monty opens. That is, the two events are independent of each other in almost every sense of the word. In conclusion, it is possible to have apparently equivalent events, such as AC and CC, that are in fact entirely disconnected from each other in the way they are updated by new information. In other words, one apparently similar event can be independent of a third, that is BG for example, while the second is dependent on the third. This will affect the relative probabilities. In our case, we found that the event associated with the car being behind the door selected by the contestant were independent of the door selected opened by Monty, whereas the events associated with the car being behind any other door were statistically dependent on the door opened by Monty. We also found a good intuitive reason for this. Thank you for watching.